for chapter 2 homework or chapter 4 homework yet, and I know I turned it in. Do you want me to just redo them?
Did I give them back to you?
No.
I mean, there's papers that I haven't graded, so.
Okay.
Yeah, if I haven't handed it back to you, then I'll probably just have it.
Okay.
Hello? This is she. Yeah. Yeah. So I've been doing it through the JCLS library, and I've been doing it through the Jackson County Library System. So I have, sorry, this isn't like a good phone. Um, sorry, I said it's not a good phone because it's like a digital phone, so it doesn't. But I was saying that my next one is at the Prospect Library on May 31st at 1 p.m. and you can check the Jackson County Library for a schedule. So Grants Pass is not part of the Jackson County Library System. So yeah, so that would be Josephine County. But it does sound like a lot of people are interested in that area. I don't know if maybe we could do something in the future with the Josephine County Libraries. I don't know. I haven't reached out to them. I don't have a relationship with them. Were you able to find my email on the website? My email? Yeah. Is my email there? Because if you email me mshepard@roguecc.edu, we could follow up about it. Yeah, so it's mshepard@roguecc.edu. Yeah, .edu. Uh, no, it's not a mailing list, but I can reach back out to you later because I have class now. But yeah, but you're not the first person from Grants Pass who's reached out to me, so there's obviously a demand. Yeah. 1 p.m. Yeah. No, you just show up. It's open to everybody. Yeah, they love it. All right, thanks. I'll reach back out to you. You too. Bye. All right, so my plan for today was, I think we're going to try to move on from the s'mores. If we need to go back to the analogy, we can. But I think we want to try to do our chemicals today. And so I'm thinking we'll just do a bunch of practice problems, maybe look at some of the homework as well, and just feel really good about that. And so I also handed out kind of the mole highway. And so this is supposed to help us as well. And so kind of, right, orient yourself, kind of think about too with the s'mores, what was going on, what was the analogy. And so in the middle is, again, right, kind of your safe space or home base is your moles, right? And you can think about with the s'mores how it was the graham cracker, you know, the marshmallow, right? We had 2 graham crackers, 1 marshmallow, 3 chocolates, and those were our molar amounts, right? And then we took that analogy the next step and we assigned them, right, a mass, so aka their molecular weight. And so then we have, right, our molecular weight conversion. And so this is just helping us go from mole amounts to gram amounts. And so just like we did, right, we could multiply our mole amounts, or you would also divide like you did again with the moles. So everyone did really well, right, with the moles and the s'mores. That all made sense. So kind of recapping, right, we had seen, okay, they gave us the quantity in gram amounts, And then y'all went ahead and divided, right, from its molecular weight, and then mole-mole ratio, so all those things. So that's just outlined here. And we can say, right, think of our molecular weights from the s'more. And so, right, we gave you the molecular weights, but y'all know how to calculate the molecular weights of all the chemicals, so you can do that. And so this is just telling you which way to go. You can also use dimensional analysis, of course. So, right, maybe put that note there. So dimensional analysis is your friend. So that's helpful. And then we'll talk about this as well. We didn't do that explicitly when we talked about the moles, but we can also go between moles to individual particles. So maybe we should practice one of those next. And we need to write Avogadro's number. Oh, it's actually here. But Avogadro's number, so this is just another conversion factor basically, and it's on your mole sheet. But you have 6.022 times 10 to the 23rd particles in 1 mole of something. And we'll get to the density thing. I don't have practice that kind of involves that, but this would just be if you have, you know, a reagent that's not water, then you'd have to account for the density potentially. So that's what this is. And this chart doesn't include molarity, which we haven't touched on. So we'll continue forward. I think it's next chapter, if I remember, is solutions, and then we'll kind of take it the next step with molarity. And so let's just kind of, we'll recap with the lecture notes, and then we'll start doing some practice. And so again, right, we're thinking of, well, we had a pizza recipe, we have our s'mores recipe. Either way, it doesn't matter. And again, right, these are just our ratios. And then y'all are practicing balancing, right, with the coefficients. So we just balance with our coefficients once we write our formula properly. And so then we can figure out, again, just like you did with the s'mores, so now taking it with molecules, so how many moles of CO2 are formed if 22 moles of octane are combusted. So go ahead and warm up with that. I won't scroll down. So how would you calculate it? have an answer? So what we get? So 176. I actually don't have the answer. Oh, you're right. So we scroll down. But walk us through. So you got the right answer. But did everybody get that? Did our brains forget everything as soon as we weren't dealing with s'mores? And so, right, let's just recap. So same thing, right? So we have, just pretend this is our happy s'more reaction and not, right, chemicals combusting. Much better if we replace everything with s'mores and pizzas. But same concept, so now we're starting with 22 moles. And so of course they have the work out here, but right, so 22 moles. And then this is just our conversion factor. So just again, going back to our balanced equation. So we're focusing on our octane, and then it asks for CO2, so we were just looking at that ratio. And remember, right, that's our conversion factor. And so then, just like we did with our happy s'mores, right, our octane cancels, so instead of, graham crackers or whatever, now we're doing octane and CO2. And then it should be 22 times 8, which gives you 176. So did we all get that? Did we feel okay about that? Yeah.
So why is the coefficient in front of CO2, the 16, in the equation it's 16 mole? Why?
Because remember, these are always moles. Like even when we were talking about our s'mores, right? Yeah, it's always a mole. So we defined it as a mole. Yeah.
Okay.
And it could be individual molecules too. It's just when chemists talking like chemical quantities, right? We're not going to be reacting one molecule with one molecule. Although there are people that do that, but that's molecular cross-beam reactions, right? So we work in just big quantities that we can actually measure. And so that's why we always work in moles, at least. We tend to always work in moles. Other questions? Ask your questions.
Wait, where are like the numbers coming from, like the 2 and all that? Any of this like things from?
Yeah, so it's back from the balanced equation, right? So that's where like the 2 comes from. So the 2 is the coefficient there, right? The 16 is a coefficient for CO2. And remember that these combustion reactions do always kind of look scary just because they do have large coefficients to be balanced, but that's just how they look, right? So just treat the numbers as they are. Other questions about where numbers came from? Ask questions now, because things will only get more and more steps in the future. And so then, right, we were doing, so this is just our mole-mole conversions. And let's maybe just add this. So this is, right, mole-moles. But again, like we had mentioned, chemists don't just work in moles, right? We can't go to the balance and it won't tell us how many moles something is, unfortunately. So it just gives us a gram. And so again, this is where the highway could come into play as well. And so if we go back to our mole highway, right, let's say we're given everything in grams. Well, we can't do anything until we're in moles. So I can't star moles enough, right? That's our safe space, our happy space. And then it tells us, okay, we want to get back to moles, and we just divide by our molecular weight, which matches, again, with our dimensional analysis. And so this is just kind of walking you through the process that generally tends to happen for these stoichiometry problems. And so, right, basically it tells you you have A is your reactant, And that means that usually you're given, right, your starting material in a gram amount. And so it's just walking you through the process. So it's saying, right, we can't calculate anything until we go to moles. And you could add, right, divide by molecular weight if that helps. Then we get moles. And then this is, right, just our mole ratio. So basically conversion factor from our balanced equation. And then ratio, that gives you moles of B. And then usually it asks you for the mass of a product. So it says, right, what's the expected yield in grams? And then you just multiply, so times our molecular weight to get us back from moles to mass. All right, so let's try that. And it kind of tries to lay out the strategy for you. So we have our same balanced equation, so still looking at our combustion reaction. And again, don't let the numbers scare you. So it says, what mass of CO2 is produced when 3.6 times 10 to the 15 grams of octane are burned? Sorry, I'll put a share link soon. Forgot to do that. So how are we doing on this? So what's step one? What are we all doing?
So we have a balanced reaction.
Yep.
That's given.
So that's a good first step.
We're going to do a two-part conversion, right? From
Yeah, so we gotta go from grams to moles, right? So other, yeah, so we got, so kind of maybe highlight what we know. So we have 3.6 times 10 to the 15 grams of octane. So we started with our balanced equation. And then, right, what's our relationship between octane and CO2? We stated it earlier when we did the 22 moles problem. Yeah, so 2 to 16, right, that hasn't changed. And we can just grab that, again, from our balanced equation. And right now, you can write that. And, write it in whatever way makes sense to you. So for every 2 moles of octane, then we have 16 moles of CO2, right? Don't forget that you can write it the other way, just like all our other conversion factors. So, right, those are just our conversion factors relating the two. And then it tries to, like, help us, but also just kind of think through it, right? So without staring at this and kind of depending, you're just looking at this. Okay, we started with grams, but then what do we say? That what's our quantity need to be in? How can we compare them? What are these related to? Yeah, moles, right? So just by knowing that, we know, well, we have to convert grams to moles, right? That's the first step. And so do we do that at least, maybe? So then we can set up, right, we have 3.6 times 10 to the 15. I'll just put grams of our octane. And so we need to go from grams to moles. And so this is where things can get a little steppy, right? Because now, unlike our s'mores, I didn't just give you the molecular weight, but you can solve it. So what's the molecular weight of octane, roughly?
114 grams.
So 114 grams.
But if we're using 2 moles
Well, don't do that. Yeah, so just keep the molar amounts, because the way you're thinking is mass balancing, which, like I said, isn't wrong, but we don't want to think that way, because then we have to think differently. And so let's just verify that so we all know how we got 114. So you can just multiply, right, all our atoms. So you look up carbon on the periodic table, it's 12. There's 8 of them, so 12 times 8. And then there could be different numbers, right? Because what if you use 12.011? That's fine. I expect there to be some fluctuation. And then plus 18 times, and you can round it to 1 or 1.008 or 1.01, blah, blah, blah. So yes, right, something like 114 is excellent. And again, right, if you have extra digits, that's fine. So our sig fig is just based off of what we're given anyways. So just try to keep more sig figs than what you're given is kind of the general rule or strategy. All right, so now we can put our conversion factor. So this is our octane. So right, for every 1 mole, oops, sorry, wrong way. So 1 mole of our octane is 114 grams. So now we get moles on top, grams cancels. And we could either plug this in, or I'm just going to keep going with the setup. And so, right, the next thing is using our conversion factor. So now we have moles of octane, but we want CO2. So then we can plug in, right, this conversion factor. So now 16 moles of CO2 for every 2 moles of octane. And then that'll give us moles of CO2, and then we'll convert to mass at the end. So let's just start with that. So 3.6 times 10 to the 15th divided by our molecular weight. So now that's moles, right, of octane. And then multiply it by our ratio, our mole ratio, so times 8. So now we have, right, that many moles of CO2, so kind of ridiculous, but I'll write that down. So about 2.5 times 10 to the 14, and again, moles of CO2. So did we all get to here at least?
And then what did you divide the molecular weight from?
Here?
Yeah.
So we divided it from what we started with, because we were given, right, the 3.6 times 10 to the 15 grams, calculated the molecular weight, yeah, and then divided by the molecular weight of octane. And so this is just a good quick sanity check right there that we can get the molar amount, but then it does ask for it in grams, so determine the mass in grams. And so we just need to multiply this by the molecular weight of CO2, but of course we have to calculate it. So what's the molecular weight? So 44, that sounds good. So 44 grams per mole. So does everybody see that, right? You follow, so 2 times 16 plus 12 roughly, so that's 44. And you could have extra decimals, right, if you took it to 12.011, whatever, or 15.99 for oxygen. And so now we can just multiply the last part, so times 44 grams for every 1 mole of CO2 times 44. And so now we have our final mass in grams. So this is on an industrial scale or something huge. So 1.11 times 10 to the 16 grams of CO2. So the stoichiometric ratio was this part, the 16 to 2. Yeah, so this is always just from your balanced equation, that stoichiometric ratio. Right, and that's just like, you know, think back to your flour to, you know, water ratio or liquid ratio in any sort of recipe, right? There's always your dry ingredients to your liquid, and they're always kind of kept in a certain ratio, so that's kind of the same idea, that that's our ratio. So let's try another problem. And so again, double check that you have a balanced equation, although I think I gave it to you balanced, but always a good first step, right? Check that it's balanced, and then see if you can go from there. So you're given magnesium hydroxide neutralizes the sumic acid according to this equation. And so it asks for mass of hydrochloric acid if you have 3.26 grams of magnesium hydroxide.
How do you make sure it's balanced, just in case it's not?
So I would just check every element, right? So kind of distribute the 2 to everything. You have this 2 goes to the H and the oxygen. But you just have to kind of check the atoms, yeah. So I would just do that, magnesium, magnesium, oxygens, oxygens, you know, 4 hydrogens, 4 hydrogens. Yeah, so what ratio are they in? So what do we get for that?
B1 magnesium hydroxide molecule over 2.
Yep. So they're in a 1-to-2 ratio. And so I don't know if y'all need some more time, but kind of like my hint, if you're stuck, right, is just calculate things that you might need to know but don't, right? Like we need probably the molecular weight of magnesium hydroxide, so you can at least calculate that. Probably need mass of HCl, and then do what she did, right? So at least writing out our ratios, so kind of putting our pieces together.
Yeah. With the equation, do we start with the grams of magnesium hydroxide that we have?
Yeah, so we're not given anything else, so really we have to start with that. And then we could start kind of walking through the problem. So then what do we do from here? So we started with our 3.26 grams, and then what can we do? Or what do we need to do, right? We can't work in grams.
We need the mass. So we can, we can add our stoichiometric as the next. No, we couldn't.
Yeah, but you were saying, so we need to get the molecular weights though, right? So let's do that. So did anyone calculate magnesium hydroxide yet? So 58, is that what other people got? So remember, we have to add everything, and then this one, so the 2 gets distributed, right? So then it's the mass of magnesium plus 2 oxygens plus 2 hydrogens. So the internet says 58, but let's calculate it together. What's the mass of magnesium? I can't read the periodic table. 24 point what? 305, and then plus, I'll just round it to 16 is okay. So 16 times 2 plus 1.01 times 2. So yeah, like 58.3. And, you know, just for reference, so like on an exam, you know, if you had calculated 56, that's fine. You know, just, I'll catch it and probably, you know, just minor penalty for that or no penalty, kind of depending how far you are. So yeah, I try to be lenient and follow your work.
Well, I feel like every periodic table has a different, like,
I know.
decimal number.
Yeah.
Like, the main numbers are usually the same, but then the decimals are always rounded weird.
Yeah, so as long as you get like pretty close to that, to like 58. So then we have our mass, and then what do you do with this mass now? So we have grams of magnesium hydroxide, we have our molecular weight.
You have to convert it to moles.
So convert to moles, so that means we divide, and again we can use, right, our dimensional analysis, so grams for every 1 mole of magnesium hydroxide. And so we could plug this in just for kicks. Oops. D8.325. So then we're here, so we have moles of magnesium hydroxide. And we don't really need to calculate it, but I don't don't know if it helps. So moles of magnesium hydroxide. And then you'd mentioned the stoichiometric ratio. So now we can do that, right? And so we have, 2 to 1. So right, moles of magnesium hydroxide goes on bottom, since we want to cancel that out and get moles of HCl. So then we could multiply this, right, times 2. So now we have moles of HCl. And of course, right, so we have moles, very good step there, but it does ask for it in grams. So now we just need to multiply by the molecular weight. And then what's the molecular weight of HCl?
72.
Oh, that sounds off.
I have 36.
Yeah, 36 and then 0.45, right?
I did 0.461.
0.46. Right, so now we multiply by our molecular weight, so by 36 approximately, 36.5 roughly, and then we get 4 grams is produced then for a final answer. And then we do have 3 sig figs, so we should round it to 4.08 grams. Questions about this one?
So the 0.111 moles is the answer you got before you converted it to grams?
Correct, yeah. And you can follow the calculator work there too. So right, we just divided by our molecular weight first, got our moles of magnesium hydroxide, multiplied it by our mole-mole ratio, and then multiplied it by molecular weight.
Molecular weight is
Yeah, it was,
Moles over, or grams over moles?
yeah, so it's always grams over moles, so then stoichiometrically, by dimensional analysis, I mean, it cancels out since you have grams, moles. All right, that's pretty good. And so let's look at our other little lecture topics. And then, like I said, we'll keep practicing with this the rest of class. And so the only thing that we didn't quite cover with our s'mores example was the theoretical yield. But we'll get to that. But we did practice, so we did write some limiting reagent problems. So you can see how they're just going to get more complicated, kind of more steps. And basically, you just end up doing your stoichiometry twice. So end up solving for each one. And then you compare, right? So if let's just go back to our s'mores example. So we didn't use grams, right? We just stuck to moles essentially, right? But we just compared. So if we have so many moles of chocolate versus so many moles of graham cracker, which one was our limiting reagent? And so there's really no way around it other than to do your whole calculation twice, right? And then compare the answers. And then obviously that could get more involved just stepwise if you're given grams instead. So then you have to go grams to moles and then compare. Same thing with that. So it just adds kind of more steps, but we'll do more practice. And then our theoretical yield, so this is always what we calculate. So what we calculate. And so what I mean by that is sometimes students get confused over where your theoretical yield comes from, but that would be like this number just here, right? So we said, oh, well, we neutralized 4.08 grams. Or if we had actually calculated like how much product, like if we had calculated magnesium chloride, that would be our yield. And that always assumes, if everything goes perfectly, 100% yield, what we get. And then, of course, I'm sure you've already seen this in lab or gotten a small taste, is, right, you don't know what could actually happen in lab, or, you know, you got your product and then it blows away in the wind or whatever. And so what you actually have, right, is what you actually are holding in your hand. And so a problem would have to specify, right, your actual yield is blah, and then you know, again, your theoretical is what you calculate. And then, you know, your problem goes something like that. You just take your actual yield over your theoretical to get your percent yield. And so just for fun reference, you usually want like 90% or above for like a good organic reaction. You know, especially thinking like profits and drug design money, that sort of thing, right? You want high efficiency reactions, especially, you know, some really complicated molecules could be 20 steps, 30 steps, and your yield, your overall yield is, you know, 20 to the power of whatever, so like 20 to the power 0.9, just to get a sense of it. So if you have a 20-step reaction and they're all 90% yield, that's still only like 15% overall after those 20 steps. So that's just kind of an idea why, you know, you want a high reaction. But then in other fields, so like we'll just say metals plus organics. So like organometallic chemistry or like throwing metals onto things, sometimes you only get like a 50% yield. And that's considered like okay for those reactions. So that just kind of gives you, again, like I said, a small flavor of what's acceptable in the chemistry world. All right, so try this other problem. And so we have ammonia synthesized by this odd reaction here. So we have 2 equivalents of NO and 5 equivalents of H2 give you 2 moles of ammonia and 2 of water. And then it says starting with 86.3 grams of NO and 25.6 grams of H2, find the theoretical yield of ammonia in grams. So we have a limiting reagent problem. So how's this problem going? So did we calculate our theoretical yield with NO yet? Are we lost? So what are we thinking? So what's the first step, right? So we have 86.3 grams of this NO. Where do we go from here? Right, what do we do in this step? What's the first thing we had to do? So convert to moles. And then do you have the molecular weight of NO handy?
30.30.
You said 30.30?
No, just 30.
Oh, 30. Yeah, that sounds good. So 30 roughly. So we have 30 grams, right, for every 1 mole of NO. Oh, sorry. Divide. I don't know what I was doing. 30 grams for every 1 mole of NO. All right, so that looks good for our setup. And then what's the next thing we have to do? So we have moles. So what do you do with your moles? Yeah, so how do we find our other moles? What do we need to use? What are we comparing it to? And it's asking for ammonia. So what's our conversion factor? What's our mole ratio that's relevant? So 2 to 2, right? And so that's easy. So right, just kind of highlight what we want. So it's asking for ammonia. So okay, we need to compare NO to ammonia ratio. And if you want it to be fancy, right, you can just think, oh, well, they're already in a 1-to-1 ratio, and you know you don't need to do anything. Yeah, so it's the same, yeah. But if we want to be, again, explicit, right, let's write out, okay, for every 2 moles of ammonia, we have 2 of NO. Okay, that cancels, you know, just so we're really clear. And so then that gives us moles of ammonia. And then, of course, we can multiply by the molecular weight. What's the molecular weight of ammonia? So 17. Yeah, and I usually just leave it at 17. And so then 17 grams for every 1 mole of ammonia. So now we can just multiply everything. So 86.3 divided by 30. And then I won't do the 1-to-1 ratio. So we have 2.87 moles of ammonia, then times 17, so 48.9 grams. So do we get that first part? Yes, no. So try the H2, or try to finish that up if we still need some more time. And then we'll look at the answer. Yeah.
To calculate, what was the second part of the, how do I say this? I guess to calculate the atomic mass of H2, you wouldn't consider the coefficient in front of it, but you would consider that it's H2, it's a diatomic, so it
Yeah.
would be 1.008 times 2.
Yep.
Okay.
Yeah. And we can start kind of, oops. And then what do we use for mole ratio?
2 ammonia over 5 hydrogen.
Excellent. So 2 ammonia and, oh, other way though. Sorry. So we need 5 on top, right, since we want ammonia. So 5 ammonia. I don't know what I'm doing today, apparently. Sorry. 2 ammonia over 5 H2. That looks good, and then multiply it by our 17 grams. So 25.6 divided by 2.02, so converting mass to moles of H2, and then we only produce 2 equivalents of ammonia for every 5. So 2 over 5, and then times 17. And so now we can compare, so we get, right, 5.06 moles of ammonia, or 86.2 grams. So any questions on the H2, how we got to this 5 amount there?
How do you find out the ratio?
So the 2 to 5 ratio?
Yeah.
Yeah, so that was from just the balanced equation, right? So for every 2 moles of ammonia, we need 5 of H2. And then we put the 5 on bottom, right, since we're canceling out our H2, and then we want ammonia, so it's on top. The 48, oh, the 48.9 was when the answer of ammonia in grams, when we multiplied the 2.87 times 17.
Oh, wait. Oh, okay.
I'm not getting that.
For what?
The final answers, or the molar answer.
The moles, so you didn't get 5 moles, or,
No, I didn't.
let's see.
Divided by 2.
So times 2/5. So did you get the 5 moles roughly, or?
Oh, I know why. I had entered 2.56.
Ah. All right. And then, so then with it, which one is our limiting reagent? So which one is our true theoretical yield? So you have 2 answers, but which one?
86.2.
So this is the larger one. So this is actually not limiting, right? Because the limiting has to run out first. So we're kind of comparing, right? So we said, well, we started with these 2 different amounts, but then this one, our top amount, so our NO, creates the least. So smaller amount. So that means that our NO is actually gonna run out first, so we're not gonna have enough NO to actually make 86 grams. So this is smaller, so we can say this is our limiting reagent, and so this will be our theoretical yield then. So the limiting is smaller. Yeah, so then this would be, right, the theoretical yield. So then if they said, so let's take it just a step further really quick and say if we got 34.7 grams of ammonia, what's the yield? So this would be like a separate problem, kind of tied to this. So then you have, okay, now we have to use, right, our limiting reagent. And then we can do that really quick. So 34.7 divided by 48.9. And then, of course, times 100 just to get it to a percent. And then, so that would be, right, like about 70%. So 70. And so, right, this number has to be given in a problem, right? So this is just a random number, so that's just given to you. Oh, this is what you actually got. Or, if you were in lab, right, you would actually weigh it out and say, okay, I have this much, but I know from my calculation I should have had X number of amount.
Isn't it supposed to be above 90 though?
That's just like if
okay.
you were like if you were actually trying to optimize a reaction, that would be like your goal, yeah. So yeah, you could say that though, it's like, oh, this is not a great reaction, right? Because it is 70%, and it's not, 90 or close to 90, it's kind of ideal. All right, let's take a 10-minute break. So we're not going to do quiz, but I do want to take the recitation time to keep practicing since we lost out on Monday. But yeah, take a 10-minute break, and then we'll come back and do some more practice problems.
stuff as much on Monday.
Okay.
So this is kind of, this is the first time I'm doing it too. Yeah. You got that today?
Yeah, she handed it out.
Okay.
Did we get our midterms back?
Yes.
The mole.
Oh, you didn't get a mole highway, so. All right,
Okay.
are we,
Can I also get my midterm?
Oh.
Thank you if you have it.
I do have it somewhere.
Thank you.
Yeah. Taylor, though, if you can't meet today for office hours, we could always meet another day or Friday. Just like email me, because usually my office hours are just after class. But if you can't make it, just email me, because I'll make an appointment with you any other time.
Okay, perfect.
Yeah. Yeah, those are just my set office hours, but I usually don't even advertise it, because by appointment is better
Okay.
for, I assume, students.
Can we make an appointment right now? Over
Yeah.
like, okay.
Yeah, either let me know now or.
Okay, I can't on Friday or tomorrow, but I could on like, I could come in the lab on Monday morning.
Yeah,
Would
and
that
we
work?
don't even need an appointment.
Okay,
Yeah,
perfect.
that's easy. I don't know where your exam is. It's probably in my office if I don't have it. I can get it after class.
Okay,
if that's
thank you.
okay.
Or I could pick it up on Monday. I have my grade online, I just wanted to.
Yeah, no, I want to give it to you, but, all right, let's start off, maybe while I hunt for the missing exam. So we had a few people leave us, but let's start with, let's do, so if we have 50 grams of silicon dioxide, how many silicon dioxide molecules do we have? And don't forget your Avogadro's number conversion factor. So you have 6.022 times 10 to the 23rd. And so this is, right, atoms or molecules, or if you wanted to do like moles of donuts, that would be fine. You know, that'd be cool if you could go to Puck's and be like, I want a mole of donuts.
You like, what the hell does that mean?
So try that out. See if you can figure that out. I'll be right back.
So you can convert, you can figure out molecules
the normal conversion.
Yeah, because since we're staying with this silicon O2, whatever.
You're gonna start with your grams, because we're given 50 grams, and then you're gonna convert to moles, so you take this highway. And then number.
And divide by the molecular weight of the silicon oxide.
Right, yeah, because it would
Okay.
be that weight, mole, 1 mole over your molecular weight,
Okay.
and that's gonna, and then you can cancel out the grams. And then you're gonna go to, number of particles, which I believe is your atoms. So you can use 6.2, what is it? 6.02 times 10 to the 23rd, to get atoms, molecules, because it's just like this universal number.
Perfect, thank you.
So did we figure this problem out?
Not yet.
We can always look at our mole highway, so it kind of helps us, right? Because we're given mass of something, and we want number of particles. So we can go from grams to moles to particles.
And particle, that word can represent atoms or molecules.
Yeah, just like things, yeah. So what information did I leave out from this problem that you kind of had to solve on your own?
The molecular weight.
So the molecular weight of silicon dioxide, and what do we get for that?
Specifically
60.084 grams per mole. Is that what other people got? We can calculate it.
Or I got 83, but.
You got what?
83.
83.
60.083.
Oh,
Yeah,
sorry.
that's-
Yeah, that's not a big deal. I was like, you got 83 versus 60? Yeah, so that looks good. And so then we can set up our dimensional analysis. So we have grams, and then divide it by our 60.08 whatever grams per mole. And so then we get moles of our silicon dioxide, and let's just punch that out. So then we have 0.832 moles of our silicon dioxide, and it's asking for molecules though, so now how do we go from moles to molecules.
Use Avogadro's number, 6.022 times 10 to the 23rd molecule over 1 mole.
Sounds good. So multiply by our Avogadro's number for every 1 mole. So our moles cancels. And so times 6.022 times 10 to the 23rd. And so that means we have 5.01 times 10 to the 23rd molecules of silicon dioxide. Oops. So questions on this one so far? And then what if I asked an extension question now and said, how many atoms of oxygen do you have? So what do you need to do? What is it asking? What are you kind of looking for?
From the final answer.
Yeah, so basically based off of this molecule, so how many atoms of oxygen?
So would it be 5.01 times 10 to the 23rd times 2?
Yep. So that's excellent. And so what I want you all to see, right, is, well, this is for our whole molecule, but then you might be asked individual portions, and then you're just kind of identifying, right, how many do we have in that molecule? So looking at our little subscript. So yeah, we just multiply it times 2, and we can set up, our same sort of conversion factor just for, clarity. So we're saying, well, we have this many molecules, and for every 1 molecule of silicon dioxide, right, it contains 2 oxygen. And luckily this one wasn't too bad. So again, sometimes those hydrocarbon problems scare people. If you have like C8H18O7 and ask you that can scare people. But so 1 times 10 to the 24th oxygen atoms.
Is that just the oxygen by itself, or is it because it asks how many atoms of oxygen, but isn't that the whole equation with the silicon in there too?
So we just use a ratio, right, to tell us how many oxygen atoms, because now we're just counting like individual oxygen atoms, right? Does that make sense? So we're saying we have 5 times 10 to the 23rd molecules, but then we're saying like how many oxygen atoms do we have total then? Yeah. Any other questions about that one? All right, let's try just some other warm-up or practice problems. Come on. There we go. So let's try this style. And so this is, again, where things can start to maybe feel overwhelming. But now it's like, how can we write out our reactions? So see if you can just set this up and predict the products. So it kind of gives you a hint. So it tells you. And see if you can write out that equation. Bless you.
I'm a little lost. Are we just figuring out like the formula?
Yeah,
or-
so we're just writing the balanced
Okay.
equation right now. So, yeah, no stoichiometry with this one, just can you write out the reaction?
If it's aqueous, is that, do we put H2O at the beginning?
No, you can just put the AQ just means that it's AQ, like after, so telling you it's still dissolved.
Do you put anything for precipitate, did you put solid?
Yeah, that's a proper thing to do. Let's see, so what do we get for the formula for barium chloride then?
BaCl4.
4?
2.
2. So barium chloride, and so that's where all our naming stuff comes back to haunt us. And then reacts with potassium sulfate. So what's the potassium sulfate formula?
K2SO4.
So K2SO4, so that looks good. And we could put little AQs just because they're two solutions, yeah. And then, so then it says we make, so what's barium sulfate's formula?
BaSO4.
So, no, you don't put water unless it's being like formed as part of the reaction, like a neutralization. But otherwise, we don't care that it's a medium. And then what's the potassium chloride formula?
KCl.
So plus KCl. And then what do we need to do to balance this?
Make sure we put all, like, don't you put the,
Put a 2 in front of the KCl.
So 2 in front of the KCl. And I think it's balanced. So 2 chlorines on this side, 2 chlorines, 2 potassiums, 2 potassium, 1 barium, 1 barium. And then I'm keeping the sulfates together just because they stayed together from the reactants to the products. So 1 sulfate. Excellent. That's good. Let's try another problem. And so now we're going to repeat that, but now let's do a limiting reagent problem. And so it starts off with write your balanced equation again, and now we have iron 2 chloride mixing with sodium phosphate, and then it tells you it forms iron 2 phosphate and sodium chloride. So see if you can do that, which I think you can, since you did pretty well in the last one. And then see if you can start doing number 2 here. So now it gives you 23 grams of iron chloride, react with 41 grams of sodium phosphate. So what is the limiting reagent?
time to practice.
I don't know, I'm about to, I'm doing it now.
How do you distribute the grams in the second one?
What do you mean?
Like, where do I put that in the equation? Like the 23 and the 41?
So this is, since it's a limiting reagent problem, right, you're basically gonna have to calculate how much sodium chloride can you get starting with 23 grams of iron chloride, and then how much can you get with 41 grams of sodium phosphate.
So it's basically like you're solving it again?
Yeah, so you basically do it twice,
Okay.
and then you'll compare. Question?
Yeah, second one, are we going to, what is this, how much sodium you want us to go grams?
So it actually doesn't specify. So if you put it in moles, like that would be okay for this problem. Yeah.
So we're gonna stop.
Yeah. If that makes it a little easier. So I went ahead and threw the balanced equation on there. So just double check yourselves and of course double check me. And then I'll let y'all keep plucking at this 2 for a little bit more. Do we have the molecular weight of iron chloride by any chance?
126.751.
And then do we have sodium phosphate?
162.94.
163.94. All right, that looks good. Do we need more time, or you want to go over it? How are we feeling?
It's at 126.751.
Yeah. If you didn't take it out that far, that's fine there too. So yeah, like 126.8 would be okay, or even 127. So iron chloride, we could divide it by the molecular weight, so the 126.75. And then did y'all compare the sodium chloride amounts for this one? Did you compare like the sodium chloride amounts for these problems? Like do the mole ratio with iron and the sodium chloride? Yeah, because you could have found, like the iron phosphate, for example, like that would still give you a limiting reagent. It's just asking about sodium, so that's why I was curious what people did. There's like other ways to solve it too, because you could also calculate like how many grams of sodium phosphate you need based off of the 23 grams and see whether that's higher or lower than what you're given. But I think it's easier to just compare our final products. And so that's what I'll do. So we have 6 moles of sodium chloride for every 3 of the iron chloride. And then I think some of you mentioned that you wanted to stop at moles, which I'm okay with as well. We don't need grams right now. So 23 divided by 126.75. So that gives us 0.181 moles of iron chloride, and then 6/3, so that's times 2. And so we get 0.363 moles of product. And by product, I mean sodium chloride. So does that sound okay with people for the first one? All right. And then you just kind of repeat that. So it does get repetitive, right? So this is our iron chloride. And now repeat again for our sodium phosphate. So again, same steps, dividing our mass by the molecular weight. And let's look at their ratio. Now it's a 2-to-6 ratio though. So we only need 2 sodium phosphates for every 6 sodium chloride. So you could also multiply it by 3, so 41 divided by 163.94, and then multiply it by our mole ratio. And so now we get 0.75 moles of product. And so which one was the least?
Sodium chloride, or I mean the iron chloride.
So iron chloride, so now we can say, okay, this is our limiting reagent. So that's good. And so now let's do another problem that's related to this. And so now it wants to know, okay, well, we found our limiting reagent. And so based off of that, how much of your excess reagent remains then when your reaction has gone to completion? So see if you can figure that out, and then we'll go over it.
Wouldn't it just be the 0.75 subtracting the 0.363 to figure out what's left over?
Well, that would give you like the difference of sodium chloride, but we want to figure out the sodium phosphate left over. But you're kind of on the right track. So have we made any attempts at this or any thoughts? What can we do?
I'm wondering, do we need, is the, in the previous problem, it gave us 23 grams of iron to chloride, reacts with 41 grams. So are those numbers still important?
Yeah, so we're still working with the same numbers, right? So it's just asking, okay, after we did this reaction, since we said, right, the iron chloride was limiting, it wants to know, well, how many grams of sodium phosphate then are left over? So how do we find the sodium chloride amount, though? How do we do that? Y'all did it.
So would you start with the 0.36 and go to moles of the sodium phosphate?
That would be another way to do it. So it depends how you want to start. So if you want to start from this information, right, we can kind of back calculate. So we know, okay, well, I can make this many moles of sodium chloride. So then we can say, well, how many moles of sodium phosphate is that, right? And then get grams from that and subtract. So that's one way.
How would you do that way?
Yeah, well, let's just do that then. We'll go through the different permutations. And so let's start with our limiting reagent. So we said we had 0.363, right, moles of sodium chloride, again, from our iron chloride reaction. And then we can just go back to our balanced equation. And so now we want to calculate those sodium phosphate used. And let me just write that, right? So we want grams of sodium phosphate. But now we can just do our same stoichiometry to calculate this, right? So let's go back to our equation. So they were in a 6-to-2 ratio. So 6 sodium chlorides for every 2 sodium phosphates. So let's just set that up, right? So then we said, so for every 6 moles of sodium chloride, we only needed 2 of the sodium phosphate. And then that'll give us moles of sodium phosphate, but we need grams. And let's see. Oh, we do have the molecular weight, though, of sodium phosphate, so we had calculated that. So the 163.94. So now we can multiply it, right, by 163.94 grams and see how that compares, right, to the 41 that we started with. Does that make sense? And you could have also just divided by 3 times 163.94. And so I get that we consumed 19.8 grams. So this means, right, 19.8 grams of sodium phosphate. So that's consumed. And since it's asking, though, for excess reagent, then we have to subtract, right, 41 minus whatever we actually consumed. So then that gives us 21.1 or 21.2 roughly left over. So now 41 minus 19.8 grams. Does that make sense? And then we could have done it another way as well. And so, right, that was starting with the moles of sodium chloride, or you could have started with your grams of iron chloride instead, and then just done, right, the mole ratio of iron chloride to sodium phosphate to see how much you need as well. And I can go through that. People just want to see the process. So I'll just say alternative method. And right, so you're going to see there's a lot of different ways to kind of get the same answer. The point is you just have this relationship of your mole-mole ratio, right? So if you find a mole of any one of these quantities, you can find moles of the others. So it's all just a puzzle, yeah.
In the last one, where did 19.8 come from?
Oh, 19.8 was what we calculated.
Oh.
So going from the 0.363 moles of sodium chloride.
You might equal, yeah. Sorry, where did the 41 come from?
The 41 was from the starting problem where it said 41 grams of sodium phosphate react. And then I'll just quickly write out kind of the alternative method, right? We could have started back with grams of iron chloride, you know, found our moles again, and then done our mole ratio. So then we could go back to our balanced equation and say, well, we need 3 moles of iron chloride for every 2 of sodium phosphate. And then, of course, multiply it by the mass of sodium phosphate again.
So it would be easier to do the way that we did the first time.
Probably, since we were already starting with moles, but
But if we weren't starting with moles, we'd have to do it this way.
yeah, so kind of, again, it's always a puzzle. So it's like, what do you have? What have you already solved for? And so I'll just kind of quickly go through this. So times 2/3, just so we can see that we would get the same answer. And so there we go again, right? 19.8 grams consumed, so same answer as before.
And the 163.94, there's nothing under that at all? It's just.
Yeah, it's just for the mole.
And both methods work in all instances?
Yeah, so it's just, like I said, it's just a puzzle, right? So they just felt like it was easier to start with moles since we had already calculated that. And that's usually a good, easy place to start is moles, but
Okay, so
yeah.
It's kind of like the equivalent to being like the two-step method for like.
Yeah, it's just like, how do you want to get there? But as long as you start to see too that, right, there's more than one way to kind of solve the problem. So just because, you know, you and your neighbor are doing two separate things, you get the same answer.
And either one on the exam would be acceptable.
Yeah. All right, yeah, that's a good place to end then. And then if you have more questions, I can stay after, or you can hit me up later. You know, the lab times are always good times for office hours or additional help. All right, so thanks again. Have a good weekend.